So we'll continue on with Unit 1, kinematics and acceleration. We will be really close to finishing up acceleration, and it'll be just kind of giving up some more understandings of it. And we will add probably the next time we'll probably add some more equations and examples, and then be really close to actually finishing Unit 1, probably in the next coming weeks. So when we look at the graphs, we have to, again, be very careful about the labeling of the graphs, and that is such an important thing. If we take this graph and initially look at it and think that it's a position time graph, what these items or these different lines are doing would definitely be different than if you actually read the variables and see that it's a velocity time graph. Okay? And so knowing what's going on is very important. And so what we're going to want to do is we're going to want to rank them from the least to greatest. Therefore, there are a few that are equal, and we would need to indicate that as well. So these motion of 5 different runners from least to greatest. Well, who's going to have the worst? C is going to have the worst because it's negative, right? It has a negative slope. And therefore, C is the worst. After that, who's next? And it's not always maybe as straightforward. Well, if C is negative, after, is there another negative? Looking at the slope is going to give you that whether kind of width is going to give you your next one. Even though the position or the velocity might be negative, the slope is going to be the same as another value, isn't it? Because E and A are the same slope, they would be equal. Just one is in a positive velocity, which just might mean they're moving in a positive direction. Velocity might be moving in an opposite direction. Their slope is exactly the same. And lastly, B and D are equal. They both have a positive slope. Therefore would have that same part, have that same weight. as we saw with the instantaneous velocity, the instantaneous acceleration equation also brings into the idea of limits and the time interval, trying to make that as small as we possibly can. Now, my graph that I made to show that is probably not the best. You shouldn't have very much of a curve on your velocity time graph. You can have it on a distance time graph. Shouldn't be too much curvature on a velocity time graph, and your acceleration time graphs should definitely have no curve or much of a slope at all. It's just kind of a positive or a negative thing. But again, trying to find the slope of a line at a specific point, just like we did with the velocity, is the route that you can take. Maybe you made measurements and your graph looks like this. And you're like, okay, that doesn't look like it should. What would be the acceleration at those points? And that's where you would come in and try and take a slope of a line. If you're in calculus, you just find the area underneath the curve and go from there. But again, we're trying to find that time interval when we're doing limits and we're trying to do that instantaneous acceleration. We want our time intervals as small as we possibly can. That's kind of the key in moving forward with those. How small of a time interval can I have? Smaller the better. Gives you a better picture of what's happening at a very specific time. Is it always easy or feasible to have an extremely small time? Nope. Then you're maybe not looking at instantaneous acceleration, but you might be looking at something similar, or might be able to make some infer some information from that. So, in this image, are we going up or down? Down? Speeding up or slowing down? Slowing down. What would our velocity be in 1 second? Bigger or smaller arrow? Smaller arrow. We're slowing down, right? How would we do that? Well, we kind of take that away. I said we're going down and slowing down. How much do we take away? Well, we usually, the acceleration, remember acceleration is the change in velocity, right? So the magnitude of the acceleration arrow would be the change in velocity, so it means it would be that much different, especially since we're dealing with a nice value of 1 second, right? So however big the acceleration line is going to be the change, meaning the new velocity arrow will only go to here. Okay. Are we still going up or down? Still going down. Speeding up or slowing down? Down. What tells us kind of this slowing down idea? The acceleration is going in opposite direction of the velocity. Okay? Again, because the acceleration is equal to the change in velocity, the arrow that we use to kind of figure out how big the next velocity arrow should be is by using the acceleration, redrawing our arrow for the next one. Still going down. Still slowing down. One second later, again, why do we do that? Because acceleration is the change in velocity over time, but if t equals 1, it's going to just be whatever the change in velocity is. Now, if t was different, would that have changed things? Yeah, it would. But so a lot of times we try to use some things that are like, okay, especially when we're trying to go conceptual with it. Okay. Still say down. Still slowing down. Okay. Now, the changes are almost becoming really small, right? So now where they're almost equal, what's going to happen on the next one? Things might be changing here. The winds of change might be. Moment in time in which the velocity might be 0. Maybe it's doing neither at that time, right? Maybe because, again, velocity is not going, but a small moment in time. Okay? What's going to happen after that, though? What's going to happen to the velocity? Should start speeding up. Now it's going up or down. And speeding up. Well, where would we see something like these crazy, weird things? Well, we can throw a ball up in the air or something up in the air. A person sometimes, maybe. Just randomly throw people up in the air. Oh, like when if you had one of those parachute things and you flop somebody up in the air. Wouldn't that be fun to do? Well, we can do this another way. Maybe some bungee jumping. Where you jump off a platform, your acceleration goes down for a moment, but then you start to slow down because the bungee cord starts going, and we're going to pull you back. And then all of a sudden, for a moment, you're going to be stopped. And then you're going to start doing what? Going back up a daisy, and then back, down, up, and down. as you go up and down on a bungee. I cannot tell you what that feels like, only that I bet you it would be lots of fun if you're into that sort of thrill-seeking manner.